Welcome. We're going to do some practice problems together. These are going to apply and transfer our knowledge that we've been learning over the past couple of weeks. So the first problem that we have is ammonia is the foundation for nitrogen and the fertilizer industry. It can be directly applied to soil as a plant nutrient or converted into a variety of common nitrogen fertilizers. What is the boiling point elevation when 11.4 grams of ammonia, NH3, is dissolved in 200 grams of water, and we're given a KB for water of 0.51 degrees per minute? Okay, so the equation that we need to use for this problem is going to take advantage of our colligative properties. So we're looking at a change in temperature because they're asking about boiling point elevation. So we're looking for a change in temperature, and we're going to just put a BP here to say that that's boiling point. And that's going to be equal to little m, which is molal, KB, which we're given here for water, and then I, the Van Hoff factor. Okay, so let's think about each of these. Ammonia is not going to partition into multiple components. It's just going to stay itself. Why is that? Well, if we think about its Lewis structure, ammonia has 3 bonds from nitrogen to hydrogen, and it has a lone pair. This molecule is not going to dissociate. So in order to calculate molality, we're going to need to use the information that's given in the problem. So this is 11.4 grams of our ammonia. Let's see if we can make that a better N. Okay, we're going to need to convert that into moles. So the way that we do that is by using our molar mass. We could calculate that from a periodic table or look it up if we're not sure. So that's 17.031 grams per 1 mole. Now, molality has moles in the numerator, but it also has kilograms of the solvent in the denominator. So in this case, we have 200 grams of water, and that's as given here. And we're going to convert that to kilograms. So there are 1,000 grams in 1 kilogram. So when we do that calculation, we're going to get 3.3468, and that's going to be moles per kilogram. Now we can check to make sure that our units are correct. The way we do that is by canceling. So here we have grams, here we have grams, here we have grams, here we have grams. We're left with moles per kilogram, and that matches moles per kilogram here, or little m, which is molal. Okay, the next thing that we need to do then is plug in our values. So here, we're going to plug in what we just calculated. So that's going to be 3.3468 little m, or molal, times kb, which is the value that we were given, 0.51 degrees Celsius per minute. Oh, per molal. Ha! That's why. So our m's cancel here. That works out lovely for us. And then the last one is the Van Hoff factor of 1. So all we're left with, so molal cancels. Note molal and minutes have the same unit, so we have to be careful there. In this case, our molal is canceling, and we're left with degrees Celsius. So that's going to be 1.7068. That's degrees Celsius. Now let's think about this in terms of our sig figs. So we have 3 sig figs here, 3 here, and 2 here. So we need 1.7. If it's 2 sig figs, it would be 1.71 if it's 3 sig figs. So our increase then would be 101.7 degrees Celsius. So the elevation would be 1.7 degrees Celsius. And that's how we would calculate this problem. Okay, so let's take a look at another problem. So this one says an alternative to sodium chloride, potassium chloride, is often used in household water softener units. Suppose you had 58.44 grams of KCl and you dissolved it in exactly 2 liters of solution. What would be the molarity of the solution? What would be the osmolarity of the solution? Okay, so there are a couple of pieces of information that we're given here. We are given a mass. We're given the chemical formula, and we're given a volume. And we're being asked to find the molarity of the solution and the osmolarity of the solution. So as a place to start, we always want to solve for moles. So we're going to start here with 58.44 grams. And we're going to use the molar mass of KCl. Again, we could calculate that from a periodic table, or we can look it up. 74.5513, and that's going to be grams, and this is 1 mole of KCl. That's going to give us 0.78 388 and that's moles of KCl. Now, in order to determine the molarity, we have to use our volume. So we're going to divide by 2 liters. And that gives us 0.39194. And this is a capital M for molarity. Now, if we're thinking about sig figs here, our answer should be 3 sig figs. So we could either give that as 0.392 molar, or we could write it as the scientific notation. Now, the next part of this is asking about osmolarity. So I have to think about when I have KCl as a solid and I put it into water, what happens? So it's going to form a potassium or a K plus ion that's aqueous and a chloride ion that's aqueous. So that's going to be an I of 2. So then to calculate our osmolarity, it's going to be 0.39194 capital M times 2 osmoles per 1 mole of KCl, which is going to give us 0.784, and that's osmoles per liter. So in this case, we calculate our molarity, and then we use that molarity to be able to solve for our osmolarity. Okay, next up, let's think about the next problem that we have here. The predominant clinical syndromes of hypertonicity are hypernatremia and hyperglycemia. The serum osmolarity normal range is 280 to 295 milliosmoles per kilogram of H2O. And normal urine osmolality is from 50 milliosmoles per kilogram of water to 1400 milliosmoles per kilogram of water. So, would you expect serum osmolarity to increase or decrease if a patient is hypertonic? Would you expect the urine osmolality to increase or decrease if a patient is hypertonic? Okay, so we're going to think about a couple of pieces here. So, when solutes are going to dissolve, right? We're thinking about the movement of water in response to those solutes. So I'm just going to draw a picture here. And if we think about something that is isotonic, that means that our rate in and our rate out in terms of the movement of water is the same. If I compare that to something that is hypotonic, then I have water that's moving into the cell at a greater rate than water that's moving out of the cell. And then finally, if I'm comparing that to something that is hypertonic, right? In this case, I have a greater rate of water leaving the cell than I do of water entering the cell. And that's my hypertonic. hypertonic. So water moving in and out of the cell at an equal rate, water entering the cell at a greater rate, water going out of the cell at a greater rate. So the question is asking about hypertonic, right? Because both of these have the word hyper associated with them. So this is the example then that we're thinking about. So let's think about this. A hypertonic solution is one that has a higher solute concentration. So I'm going to type that here because I think that will help us. So a hypertonic solution is one that has a higher solute concentration. Another way of saying this is hypertonic means water moves out of the cell Okay, so if we think about the information that we were given, our normal range for serum osmolality is 280 to 295, and then urine osmolarity is 50 to 1400. So normal conditions are things like water loss through sweat. Sometimes you can have that as gastrointestinal. So for our example of hyponatremia, an increase of sodium in the blood or extracellular fluid, that means that our serum osmolarity would increase, right? For hyperglycemia, right, an excess of glucose in extracellular fluid, our serum osmolality would also increase and our urine osmolarity would increase, right? So this depends on lots of factors, right? It depends really on the level of hydration. But for both of these, right, we would expect the serum osmolarity. So let's type that out. So serum osmolarity would increase. And urine osmolality would also increase. And both of those, right, are because they're measures of concentration. So our concentration inside the cell would increase. Okay. So that gives us an opportunity to kind of think about solutes and concentration. Let's go back and think for a moment about water activity. So the question says, why is it okay to store peanut butter with a water activity of 0.7 in a cupboard, but cheese spread with a water activity of 0.95 should be in a refrigerator? So foods with a water activity above 0.95 are going to provide enough moisture for the growth of bacteria. So if we're going to answer this question, really what we're thinking about is food safety. So food safety in this case allows us to say, okay, peanut butter has low water activity. Make that just a little bit bigger. So the availability of water to support bacterial growth is minimal. Cheese spread has a water activity of 0.95. So it provides enough moisture for the growth of bacteria and yeasts and mold. So, what is water activity? Well, let's be really clear on our working definition. So, water activity is the ratio between the vapor pressure of food and the vapor pressure of distilled water under identical conditions. So at the same temperature, at the same pressure. It's important here to note that, right, our water activity increases with temperature, which makes sense because, right, we're looking at vapor pressure. And, right, we can think about this as the equilibrium relative humidity. So really, water activity affects food stability. The lower the water activity, the more shelf stable the food is. A value of 0 means there's no available water, whereas a value of 1 means that it's mostly water or pure water. All water is available, is another way of thinking about it. So generally, foods with water activity of 0.85 or lower don't require refrigeration. But as soon as you get into the 0.90, 0.95 range, that's when you want to be able to refrigerate because you don't want to promote the growth of bacteria, yeasts, or mold. Okay. Let's take a look at another problem. So we talked about the Stokes radius or the Stokes-Einstein radius. And this is of a solute, and it's the radius of the sphere that diffuses at the same rate as the solute. So it's related to how solutes move or their mobility, factoring in not just size, but also the impact of solvent. A smaller ion with stronger hydration, for example, may have a greater Stokes radius than a larger ion with a weaker hydration. This is because the smaller ion drags a greater number of water molecules with it as it moves through the solution. So we're going to draw the hydration of a large ion compared with a smaller ion. So it's important here. Let's make sure we have a shared definition of the Stokes radius. So Stokes radius is the effective hydrated radius in solution. Ooh, sorry about that. In solution. Sometimes this is called the hydrodynamic radius. Okay, so here's an example. We have a sodium ion, or Na plus, and we're going to think about the orientation of water molecules. And we're going to think about the general size and fit of these. So I'm going to approximate this with a triangle. And we think that we can fit approximately 5 triangles around sodium. So the radius of our sodium ion, if we were to look it up, It's not something you would necessarily know, but R of Na plus is equal to roughly 0.1. It's actually 0.102, but 0.1 nanometers. And so on average, it can fit about 5 water molecules. All right, so we're going to compare that, right? So this is our smaller hydration shell. Make sure to label that. We're going to compare that to magnesium. So Mg has a radius of 0.065, so it's going to be smaller. And this is 2 plus. But it can fit 15 water molecules. So if I'm thinking about the number of triangles that I can fit here, it's 4, 5. Ooh, this is getting tricky to draw. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, ooh, 13, 14, and 15. All right, so this one has an R of, this is Mg2 plus of 0.065 nanometers. And it can fit about 15 water molecules. So if we're thinking about this, right, the effective charge, because we said this is bigger. And I'm sorry that my drawing is not perfect to represent that. It should actually come kind of out to here, but I didn't make my triangles big enough. So if we want to think about effective charge, what we can really say here is that an R that is 2 plus, right, relative to an R that's just plus 1, relative to an R, relative to an R that has a minus 1, relative to an R that has 2 minus. So if we add electrons, that's going to result in the ion being larger than the atom. So adding 2 electrons has an even greater effect. But removing electrons means the cation is going to be smaller. So when in water, the ions attract water molecules, and that's going to make the hydration shell the higher the charge density. So the more water it attracts, the bigger it's going to become in water. Okay, that's a cool visualization of an idea we've been talking about. Let's take a look at a slightly different problem. So water in the US can contain natural calcium fluoride along with other calcium and magnesium salts, according to the CDC. But fresh drinking water does not contain fluoride unless it's added. The ingestion of fluoride during pre-eruptive development of teeth has a karyostatic effect. It reduces dental caries, or it reduces cavities due to the uptake of fluoride by the enamel. Determine the KSP of calcium fluoride, CaF2, given its molar solubility is 2.14 times 10 to the negative 4. Okay, so the first place we're going to start is the information that we're given in the problem. So we know that CaF2, when it's added to water, is going to solubilize into Ca2 plus, that's the aqueous ion, and 2F minus. Okay, so that means that our KSP, or our solubility constant, is going to be square brackets because that represents concentration, Ca2 plus, and 2F minus squared. Okay, so if we think about that, right, it's a 1-to-1 molar ratio between our calcium fluoride and our calcium 2 plus ion, but there's a 1-to-2 molar ratio between our calcium fluoride and our F minus. So if we want to think about this value, then 2.14 is our molar solubility times 10 to the negative 4. So that's our calcium. Put square brackets around that. And then we have to double that concentration, so it becomes 4.28 times 10 to the negative 4th. Ooh, and I should add molar here because it is concentration. The square brackets tell us that, but it's better just to be clear. And then that's going to be squared because we have to be attentive to the 1-to-2 ratio. So our KSP then is going to be equal to 3.92 times 10 to the negative 11th. And remember that our KSP is unitless. There are no units. And if we take a look at the problem, we have 3 sig figs. So 3.92 is appropriate. So this is just calculating similar to what we've done in class to determine solubility, but now we've been given the solubility and are asked to find KSP. All right, the next problem that we're working on is a solvent dissolves solutes. Water is called a universal solvent because it is capable of dissolving many substances. Explain why the chemical composition of water and its physical attributes make it such an excellent solvent. Use a claim, evidence, and reasoning statement, or CER, where the claim is water is called the universal solvent because it is capable of dissolving many substances. You need to provide the evidence, at least 3 examples of water acting as a solvent, and the reasoning, the scientific principles for why water is an efficient solvent. Okay, so let's tackle this one. So our claim water is the universal solvent because it is capable of dissolving many substances. Okay, so let's take a look at our evidence. Now, you might have come up with different examples of evidence, but here are the ones I was thinking about. So, example 1, water disrupts the attractive forces that hold salt, like NaCl, in a lattice. The salt crystals are dissolved by water molecules, creating aqueous ions. Here's example 2. Water hydrogen bonds to many hydroxyl groups found in sugar or carbohydrates, like glucose, which dissolves the sugar. And then example 3, phospholipids, like water, because they have polar heads, often carboxylic acids. The polar heads interact with water and the hydrophobic tails form micelles. All right, so let's think about our reasoning then. Our reasoning is what connects our evidence to our claim. So, what do we know about water? Water molecules have a polar arrangement. That's where the hydrogens are partially positively charged and the oxygens are partially negatively charged. So this is due to differences. Oh, I've got 3 R's there. Sorry about that. Due to differences in electronegativity between oxygen and hydrogen. So water can then be attracted to many different kinds of molecules. And if you want to go further, you could talk about how molecules that like water are hydrophilic. Nice. So that gives you an example of a claim evidence reasoning that you can use. Okay. Those are just some examples of practice problems related to the concepts that we've been covering so far. Thanks again.